Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the very good stuff. This is the IOP AAS ebook series. And I'm very happy to have ebook author Jim Kolata with us today. Hey, Jim.
Hello. Nice to be seeing you finally, even though by Zoom.
Even by Zoom. We'll take it these days. We will take it these days. Jim, what's your geolocation? Where are you at?
Well, right now my home is in Chicago, right across from Soldier Field.
Okay.
And I'm looking down at the LSD, Lakeshore Drive, which the name has now been changed, but and also there's a railroad track between us and the stadium there. But we have a nice downtown location.
Oh, very nice. Yeah, I lived in Chicago land for about a decade. I probably spent 5 years in that downtown area, and that lovely background image that got behind you there. I was on Dearborn Street by the river. And I don't ever recall in my time in Chicago seeing an estuary basically in front of the city of Chicago. So is that real, or is that photoshopped, or what is that?
No, that's absolutely real. That picture was taken from Northerly Island, which was actually put together for the 1933 World's Fair here. Mm-hmm. But then afterward, it got turned into an airport for rich people. Right. Although there were even some commercial flights. I remember coming in on a commercial flight into Meigs Field back in the 1960s. Mm-hmm. But then Richard M. Daley decided that it was too valuable a piece of property to be given over to rich people who have airplanes. And so one night he brought out a construction crew to make X's in the runways, and people had to take their planes out via trucks. And then they tried suing him, it didn't work. And then he turned it into a very, very nice area for migratory birds and a prairie location. It's really a fantastic place. If you ever come, I can take you on a tour of Northerly Island.
That would be great. That would be great. Yeah, because when I was still there, it was still Meigs Field. So that's pretty interesting development. Chicago politics, you gotta love it, right? Middle of the night.
Oh yes, yeah. Well, that was Richard M. for you. Richard J. was also that same type, but
right. So. Oh yeah, no, the apple didn't fall too far from the tree on that one. So very interesting. Cool. So Jim, what do you like to do for research or education these days?
Well, my training is as a nuclear physicist, and my research is basically in the interactions of exotic nuclei that live for only fractions of a second. And I retired actually a number of years ago, which gave me the opportunity to write this book. But I'm still doing research, and in fact, this weekend I'm going back to Notre Dame to do some experiments in our laboratory there.
Cool, very nice, very nice. So, what gave you the idea to do this particular ebook?
Well, actually, what happened was back in 1989, would you believe, I was approached by the physics department, or at least a number of us were approached by the physics department to develop courses for non-science majors. We had only really one course for non-science majors, and it was really a sort of a high school course, maybe at a slightly different level, and it wasn't very popular. Of course, we had the usual graduate courses and courses for majors and engineers and things like that, but we really needed to expand our repertoire. And so I thought, boy, cosmology is a fantastic subject. And what's really great about it is you can tell people about the scientific method and show them how cosmology is almost the perfect exemplar of how the scientific method works.
Cool.
And the other thing about it is that you can do it, well, as you know, cosmology is a very heavily mathematical subject, but I found that you could do a lot without very much mathematics at all. And that turned out to be extremely popular for the students.
Cool.
So over the years, I developed a number of notes because my interest was to extend beyond the discovery of the Big Bang. There were a lot of good books at that time that were at the level I was aiming at, which is non-science majors. But they tended to stop at the Big Bang, and also they tended to be more historical, concentrating on the people rather than on the science.
Yeah.
So, and there was nothing that I could find beyond the Big Bang model. So I developed all these notes. And then when I retired, I had them all, and I thought, wow, this would be make a great ebook. So that's how I got started on it.
Cool. And so from when you sort of inked the deal that you were going to do this to when the first edition came out, how long did that take?
Well, it took about 2 years, but the real intensive work was only about 1 year, because I had a lot of those notes in the form that they were relatively easy to convert into an ebook. So it wasn't as difficult as I thought it might be.
Okay. And how about the second edition? Did that go?
Well, the second edition came about for two reasons. One is that I envisioned the book as an ebook. And as a result, I had very few figures in it. I figured that would just make it more expensive for the print edition. And people who were really interested could get to the ebook. So in the ebook, I put in a lot of links to places they could go to extend their subject matter beyond what I could talk about in the book.
Cool.
That worked out very well for the ebook, but then I realized that the print edition, they didn't put those links in, and so there was a lot missing. So that was one problem. And the other one was that the ebook original version came out just as gravitational radiation was discovered. And I had talked about that in the first edition, but there was nothing to say beyond, oh, something great will happen. So I added that in the second edition, plus a lot of additional figures.
Oh, that's great. Super. So why don't we go ahead and do a little preview walkthrough of this very lovely ebook. And we'll start it off on the title page. Elementary Cosmology, from Aristotle's Universe to the Big Bang and Beyond, by James Kolata.
Right. I wanted to start with the early Greek philosophers because it wasn't generally known how much they knew about what they thought of as the universe at that time. For example, the radius of the Earth, the distance to the moon, the size of the moon, all of those things were known to a pretty high degree of accuracy back then.
Yep.
And then, of course, there was a period from Ptolemy until the Renaissance where nothing much happened in the Western tradition. But I then covered that material and took it from there up to the discovery of the Big Bang. And then I went beyond that.
Very good. Let's go ahead and maybe let's just walk through the table of contents. That would be good. Second edition, ebooks. Ethan Vishniak is editor-in-chief for this. Steve Koaller sort of heads up the committee that's driving these ebooks. There he is. There's Steve right there. And we have a video with Steve, so I'll put a link to Steve's talking about ebooks in the description below this video.
Okay.
So we'll do that. We got the cover page. There you are at Notre Dame. Cover material and some great quotes. And we'll get to the table of contents. All right, so let's just sort of walk through maybe some of the things you want to talk about in the Table of
Yes.
contents from a broad view? Mhm.
Sure. Well, I started off with an introduction to the scientific method because um, it's very important. It's important to know that when people say it's just a theory, not a fact, that's very different from the way scientists view any science, but especially cosmology. And then some mathematics. Well, I described the course to the students as being for those who are not mathematically inclined, but I had to incorporate some mathematics.
Sure.
In particular, I had to tell them about the use of scientific notation in cosmology, because one of the distinguishing features of cosmology is not only do we talk about the biggest things in the universe, it turns out we have to talk about the smallest things in the universe. And to cover that huge range of distances, we need to know about the exponential notation. And then the third part was exponential growth, because really that I wrote that at the time of the COVID virus and all the discussion of how fast growth is. And people really, in my estimation, didn't really understand what exponential growth really meant. And so I spent a bit of time just showing how exponential growth is just a remarkable thing to really understand.
Yep.
So those are the first three parts of this chapter, which are of this book, which are really just an introduction to what I need to do for the rest of the book.
Cool. Good.
And then early astronomy really covers things from Aristotle and the other Greek philosophers all the way up through Newton, showing how our idea of the size of the universe changed over time, and where we were at the time of Newton, as far as what was the understanding of the universe. And of course, I had to introduce a few equations there, like Newton's theory of gravity and the second law, etc. And then I went on to the nebulae. It turns out they were key in understanding the size of the universe. What wasn't understood at the time was how many different types there were. And it was important to understand what these were. So it's a relatively short chapter, but it shows that for example, the spiral nebula, which are, we now understand are other galaxies. At the time, of course, it wasn't understood, but even in the late 1700s, there were speculations that those spiral nebulae might be other universes, just like our own. But it turned out that you couldn't really show that until you could measure the distances to these objects, which was really the topic in the next chapter, where I talked about the cosmic distance ladder, going from the parallax to the supernova scale that gives us the largest distance scale that we can use. And then I mentioned the spiral nebulae and how they were now shown to be extragalactic, and then how astronomers could measure the chemical composition of the stars. All of those were, I thought, really fascinating subjects and I think that the students agreed with me. But that was sort of really the introduction to the rest of the book. And to go from there, I had to talk about at least a little bit about the special and general theory of relativity and the discovery of the expansion of the universe. And so that was this next chapter. And then finally, the next two chapters were what led to the discovery of the Big Bang. There were actually three different discoveries of the Big Bang, but only in the third one were any people willing to invest in the truth of the theory. And that third one was the smoking gun, the cosmic microwave background radiation,
Yep.
which was finally discovered in the 1960s. I can remember in grade school learning a little bit about cosmology and the steady state theory of the universe, which was very popular at that time. And then when I got to college, everything turned around because I was a freshman in 1960, and by the time I was a senior, cosmic microwave background had been discovered, and everything looked completely different. So I spent time there in this seventh chapter talking about the importance of this cosmic microwave background, which basically gave us an idea of a new idea of how the universe works.
I would say the discovery of the CMB generated a lot of second edition textbooks, third edition textbooks. And I think we'll probably touch on that topic by the time we get to the last topic here in this ebook. So
sure. And then I did sort of a backward step because I, at that point, had to talk about dark matter. The idea being that we want to know, for reasons that came up somewhat later, we want to know how much matter there really is in the universe, because it turned out that that it affects this expansion of the universe in a very specific way, and a very large fraction of the second half of the 20th century was astronomers and cosmologists trying to figure out how much matter there really was in the universe. And it became clear after, there were several discoveries of the fact that there's matter in the universe that we can't see, but it was Vera Rubin who really pinned it down. And her work showed that there was a lot more matter in the universe than we could actually see. And then later on, it was shown that not only was there a lot more matter in the universe, but the majority of it was actually this exotic form called non-baryonic dark matter, which people are still trying to understand. So that's what this chapter was, because I needed to put in some information on how much matter there was in the universe, because it was so important for what the evolution of the universe was, how it happened. Okay.
yes.
Well, then excuse me. The next topic was actually sort of comes sort of from my area of interest, nuclear physics. It's nuclear astrophysics. And I started with Steven Weinberg and his first 3 minutes of the universe. And the idea of nucleosynthesis and how nuclei were actually formed in the universe. Now, it turned out that his book, First 3 Minutes, was in the form of a movie of the evolution of the universe, in which each frame is at a factor of 100 longer time than the preceding frame. And I'm sorry, a factor of 10 longer time than the preceding frame. And he lays out what was the understanding of the of the universe, situation in the universe at the time from 10 to the minus 2 seconds until 100 seconds after its formation, at which time nucleosynthesis in the Big Bang was basically complete.
Yep.
And so I just laid out his theory, or the various chapters of his book, to show how the universe evolved at these very early times, and how that ended up making the nuclei that we observe in the everyday, but not all of them. It turns out, in fact, only a very few of them were actually formed in the Big Bang from, hydrogen through beryllium. So the Z=1 through Z=4 nuclei, and the beryllium actually decayed away. So there were only hydrogen, helium, and lithium formed.
Right.
And so we go through all of that and show how that worked. And then in the later frames, we talk about the cosmic microwave background and the fact that at the very early times in the universe, including the time when the nuclei were formed, the universe was actually opaque. So we can't see back to that time because it was so hot that it was like the surface of the sun. Mm-hmm. And but at about 400,000 years after its formation, it cooled down enough so we could actually see what was going on. Mm-hmm. And that was covered in that section.
Cool.
Well, it did cool, yes. And then the next section of that was the birth and death of stars, because the natural question is, if only lithium, hydrogen to lithium is formed, then where is the rest of this stuff coming from? And the answer to that was finally understood because it was actually cooked up either in the center of stars, which exploded and polluted the universe with these heavier elements all the way up through actually even plutonium, or they come from the actual energetic explosion of the stars itself. And the nuclear astrophysicists have been pretty successful at figuring out how much of each element was made in these processes, even though this is still a vital part of nuclear astrophysics, trying to really understand this process at a very high level of ability to understand. And then the last part of that was the size of the universe. The fact that we really don't know how big the universe is, but we do know something called the visible universe. And the visible universe is just related to the fact that the universe we know is about roughly 14 billion years old. And since the speed of light is the fastest thing we know, then light can come to us, it would seem, from only, let's say, 14 billion years away from us, and therefore from 14 billion light years distance. It turns out it's more complicated because the universe is expanding. So in fact, it's something more like 90 light years across the universe. But that's what's called the visible universe. We can't see beyond that, even though there may well be other things out there. It's just the fact that light is the fastest thing in the universe. And so when we look back in time, we also when we look at large distances, we look back in time, and so we can only see out to a certain distance.
Yep. All
right. Well, that really covered the first part of the course. This was a one semester course, first half of which is to talk about the Big Bang theory and the formation of the nuclei in the in the early and later universe. And this is where we go beyond the Big Bang, and we're, instead of now talking about the biggest things in the universe, we now talk about the smallest things in the universe, because now we're trying to understand the nature of the Big Bang itself. Where did it come from? How much do we understand? How well do we understand how it proceeded? We can only go back, let's say, by visual observation to about 400,000 years after the Big Bang. Is there any way we can go back even further in time? What's the way to do that? And so what I needed to do was to talk about the forces of nature, and then the quark model of the universe, and then the leptons and gluons, these exotic particles which make up the micro part of the universe. And then we can talk about the history of the universe from the very early frames before the times we had talked about in the like 10 to the minus 2 seconds. And that is the object of these next 3 standard model: history of the universe, and why we have matter rather than antimatter in the universe. So at that point, I then discussed problems with the Big Bang, with our understanding of the Big Bang, and that's the next, well, I guess here, 4 topics: the so-called horizon, flatness, smoothest, and magnetic monopole problems with the Big Bang, which would take some detail to go into, and so I probably won't do that, but I'll introduce then our modern understanding of how the Big Bang could actually have happened. And this is the so-called theory of inflation. So this is where my business majors get into this course, how inflation solves all of our problems. They love that.
I don't know about that, but that's a very different inflation. Yeah, very good.
So then after I did that, then I had to talk about the fact that back in 1998, this problem of the nature of the universe, in fact, its curvature, what it looks like on a large scale, and the fact that that's related to the amount of matter in the universe, that whole business was completely destroyed when people found that the universe, instead of slowing down as you would expect as gravity draws in all the material from the universe, instead of that happening, which is what people had thought was happening, the expansion is accelerating. It's getting faster and faster and faster. And how could that be? Well, of course, we always have an explanation. We call it the dark energy, okay, which is completely unknown, all right?
Right.
It is, and people are trying very hard to understand it, but it's simply not understood yet. And that's actually fantastic, because what I wanted to get across to my students is that, gee, if we knew everything, physicists, astronomers, we'd all be out of business. There's nothing new to study, right? And there was a time in the history of physics where people thought that was the case, but it's certainly not true now. There's so much more we don't understand that it's just incredible. And that's one of the fascinating things about science, and one of the things that students didn't really understand. They thought science was something you read in textbooks, not something that's living. And they thought that, scientists had theories that were all written down and they knew everything. And if they changed their mind, there must be something wrong with science. But it's just not true. We discover something new, and that's great. We love to discover something new. And dark energy was certainly something fantastically new.
Indeed.
I'm sure you understand that when you
Yep.
when you do your work. So then now we get even deeper into this whole business. The idea of this inflation leads to attempts to understand how this happened. And it turns out that the modern theories of how this might have happened are so-called field theories, which are theories which indicate that the universe, instead of having 4 dimensions, well, the 3 dimensions we're familiar with plus time, which Einstein showed was a 4th dimension, that really to understand what's going on, it seems like the only way we can do that is by adding additional unobserved dimensions into the universe.
Yes.
And so that whole chapter on higher dimensions was an attempt to show how that works, why, even if there are, let's say, 11 dimensions, why the extra dimensions can't be observed. All of that is fairly well accepted at this time, but of course, that's again an area where people are really heavily studying what the heck is going on here. What's the reality of these higher dimensions? Can we actually observe them in some experimental way instead of in theories? Fantastic area of study in the area of cosmology and high energy physics. And then one of the ways that people are trying to understand this is by looking for a quantum theory of gravity, which would sort of unify all the forces in the universe. We have unified theories of the forces in the universe, which have one outstanding problem, and that we don't have a quantum theory of gravity. And so this whole idea of string theory is trying to come up with a quantum theory of gravity. Some progress has been made, but there's a whole lot of things that's not understood. And so I, for example, have links to videos in which very nice videos which show what is understood and what isn't understood about this lower layer, about this very small level of the universe.
Okay.
And then we're finally getting to the last couple of chapters here. I had to introduce neutron stars and black holes here. In the previous version, I had them earlier, but here I wanted to put them into perspective because it turns out that gravitational radiation is closely coupled to the physics of neutron stars and black holes. And in fact, that's really the study that's going on right now. And so I had to tell people about neutron stars and then black holes, because they're so important for gravitational radiation studies. And of course, that leads to things like Hawking radiation and thermodynamics of black holes. Fantastic, interesting subjects, although not closely related to cosmology. And then finally, the end, the one chapter that I added to this was gravitational radiation, because it had been discovered by the time I wrote this second edition. And it just had so many fantastic things. It gives astronomers a new way to look at the universe. Previously, the only way we had to look at the universe was with light. And now we can look at it with gravity. And it turns out there's a tremendous amount of information you can glean from the universe by looking at it with both light and gravity at the same time. And so that's a truly fantastic study going on right now.
Mm-hmm.
So that ended the book. And then as in my earlier edition, I had a study of a reading list of about 100 books that people could go to, all of which I have read over 30 years, by the way,
Yeah.
and in which they could learn things about cosmology that I didn't have the time to tell them. And then the next section was links to astronomy and cosmology websites, links to, for example, virtual telescopes and all sorts of fantastic things that describe what astronomers are doing right now to study the universe. And then the last chapter was just because I had introduced so much terminology and abbreviations I needed to tell people about what those things actually meant. So that basically, going through it, is what I did. As I think I mentioned in the second edition, I put in a lot of figures, but I retained in the ebook version, I retained the links. Unfortunately, as before, the print version doesn't have all of those links. So get the ebook.
Get the ebook.
Or both. Actually, it would be nice if people had both of them.
There you go. Very cool.
So,
Yeah, very nice. So we got 154, all that in a scant 154 pages. That's pretty good. Yeah. So it seems like you've been through 3 revolutions, right? So one was, you mentioned the CMB, and then the second one you mentioned was the accelerating universe. And then the third one was, space-time is dynamic, gravitational waves. So very nice.
You didn't even mention the Copernican revolution.
Oh, okay. That's before both our times.
Right, but it's in my first chapter. So.
It's definitely there. So let me ask, well, number one, thank you very much for walking us through the contents of your lovely ebook. And I'm curious, going toward the future. So for example, a lot of the book is on the past and the present. Could you imagine, for example, I'm just making this up off the cuff, could you imagine a third edition where you go after the future of the universe, the long future?
Well,
Technology of the future.
I could imagine such a thing, but I think I'd have to wait a while before, until we get some exciting discoveries, some new exciting discoveries. You astronomers have to go out there and find some new things, and the particle physicists have to discover, for example, if they could come up with a real experimental evidence for string theory, that would be a revolution that would be worth writing about.
You spoke that like the true experimentalist that you are.
That's right.
All this other stuff, showing some experimental results.
There's always a tension between theory and experiment, but that's what keeps things going. I mean, there are so many cases in which theory led experiment, and then the other way in which experiment led theory, although I think that second version is the one that's more common.
More common, I would say. Yeah, definitely. So very cool. Very nice. I'll look forward one day to maybe that future third edition when you get the fourth revolution or fifth revolution coming along.
That'd be great, especially if I'm still around at that point.
I wish you the best. And stay in Chicago. Chicago is a good life.
Yeah, it's a wonderful place. We have water here, and we have nature.
Apparently, you have nature in downtown Chicago. It's pretty.
And I really like living in a city. Except now during the pandemic, it can be a bit of a problem. But
sure. Chicago's
in pretty good shape. I'm not that seriously worried about it.
Good, great. Well, I hope everything gets better for everyone in that regard. Yeah. So Jim, I want to thank you very much for walking us through your very lovely ebook. And everyone, I
Thank
hope
you.
this made your astronomy day just a little bit better, and consider adopting the ebook for your courses. All right. Thank you so much, and we'll see you on the next one. Bye-bye.
Hey, bye-bye.